Okay, let's see if I can get all these screens to do the right thing. Okay, here we are. All right, hi, I'm Rich Ozer. I'm at the Chabot Space and Science Center 36-inch research reflecting telescope, and it's time for our virtual telescope program. And there's John Curry. And Gerald, where are you?
Hi.
Oh, he's grainy again tonight.
Yeah,
Oh,
5 minutes
no.
ago, I was not grainy.
Yeah.
I don't know, man.
Well, that's the way it is, but sometimes it clears up. It's kind of
Well,
like
that's all
acne.
right.
It's like acne.
If I was clear, I'd probably scare off the kids, So
Yeah, I don't know. All right. Well, we've got an interesting program for you tonight. You'll notice it's a pretty bright moon, so we're not going to go for any, super dim challenge objects, but we do have one challenge object we're going to go for later, a little bit later in the program. We'll let Gerald talk to you about that.
yeah,
But we're going to start with the moon, right?
yeah, I think so. But before we start, we just want to remind everybody that we want to encourage you to donate. There's a donate button on our Facebook page, or you can go to Chabot's website, chabotspace.org, and there's a donate button up at the top of the web page. Chabot Space and Science Center is currently closed because of the pandemic. We plan on reopening next year. But in the meantime, we're offering a lot of good virtual content like the program tonight. And we are doing programs on Friday nights and also during the week in the daytime for schools. So to help support those programs and keep us going and making sure that we offer good content to the public, we do ask that you try to help us out by making a donation. And we've got a really cool deal going on right now. If you go to the Chabot website and go to the membership page and sign up for a membership, not only will you get a membership, but Chabot has got a program they're doing right now for every new membership between now and the end of December. They're also going to give a membership to a local teacher. So that's a great opportunity not only to benefit Chabot, but also to benefit our community teachers. So please help us out. Check out either the donation button on our Facebook page, donation button on our website, or go ahead and sign up for a new membership and help out a teacher. All right.
Richard, we have a complaint that you're more than grainy too. I don't think you have enough light over there.
Yeah, that's the problem. That's definitely the issue for me. I've got a big bright red light in my face, but
we're in different positions tonight to be better
socially distanced. Yes. Right. Yeah, because of the increased recommendations, we have moved ourselves apart farther in the observatory, and I'm under very low light conditions. But, it's okay.
Well, let's go to the moon.
You'll see me some other time.
Let's go to the moon here.
All right, let's look at something better than us, which is the moon.
So we're in here in our observatory. We have 3 observatories here at the Chabot Space and Science Center, and we're in the newest one. This is our 36-inch reflecting telescope, the one we call Nellie. And right now, Nellie is pointed to the moon, and Richard has got a camera.
It'll take me a few seconds to get there.
Richard's got a camera mounted on the telescope, and it'll take him a couple of seconds here, but he'll go ahead and show us some live views of the moon. In the meantime, while he's doing that, I wanted to tell you a little bit about a new spacecraft that's on its way to the moon right now as we speak. It just launched a couple of days ago. This is a Chinese space probe. It's called Chang'e 5. And it is headed for the moon, where they are going to take samples from the moon and bring them back to Earth. So it should arrive at the moon in a couple days. They're going to collect the samples, and then they're going to take off again and head back to the Earth. They're actually going to do a in-orbit rendezvous, much like the Apollo program did, and bring the samples back. They expect to bring the samples back to Earth on December 15th. So that's kind of exciting.
Worth noting that it is not manned, by the way.
Right. It's unmanned robotic mission.
Yeah.
I should say uncrewed. We can't say unmanned anymore. We have to say uncrewed.
Uncrewed, right?
Yes, yes. So
unless we're very crude.
Yeah, right. So as soon as Richard brings up those images, we're going to show you actually where it's going to land. So Richard, I'm going to move the telescope around a little bit if I can. You see that bright patch up in the upper right? That's the crater Aristarchus. Now, Aristarchus itself is an impact crater, but right next to it, there is an old volcano. And in fact, there's a channel that was cut by a stream of lava. And the end of that channel kind of widens out, and we call it the Cobra Head. But north of there, and I'm going to shift a little bit more here. And Richard, we're going to have to maybe brighten things up here just a little bit.
I'm working on it. Mm-hmm.
So the region we're looking at, there you go. The region we're looking at is called Oceanus Porcelarum. And then at the far right is the Imbrium Basin. And if you look where the Aristarchus impact crater is, that bright object near the bottom, and then you go up a little bit, you can just barely make out a kind of a dark patch with a crater next to it. And that is called Mons Rumker. Mons Rumker is another volcano on the moon, another dormant volcano. There's no more volcanism on the moon today, but a long time ago it had volcanoes. And that volcano is called Mons Rumker, and that is where the Chang'e 5 is going to land, right at the base of Mons Rumker, and collect some samples and bring it back to Earth. So that's pretty cool. Now, going back to Aristarchus, I mentioned that there is an old volcanic caldera there. And every once in a while, astronomers report seeing either a bright flash in that region or hints of smoke in that region. And we're never able to get enough to actually prove it and confirm it and things, but there have been repeated reports from that area. And the suspicion is that that volcano, that volcanic region right there, may still be a little bit active. We're pretty sure that the molten interior that once existed on the moon is long gone, but it's possible that there may still be some pockets. And so there's a lot of speculation about Aristarchus and that region around it, that there may still be a little volcanism going on there. So anyway, kind of keep an eye on the news, and you'll see here in a few days some news about Chang'e 5 bringing samples back to the Earth. All right.
Did you mention what the cause of that volcanism is? Is that tidal or?
Well, I'm not sure whether it would be a tidal effect, although the moon used to be much closer to the Earth than it is today. The moon is actually slowly creeping away from the Earth, about a little over an inch a year. And so a long time ago, a billion years ago, it was much closer to the Earth. And it's possible that at that point, the tidal forces on the moon may have actually caused some volcanism. So that I wouldn't be surprised if that was the case. I don't know that this particular volcano was because of that, but we do know that very early in its history, the moon had a molten interior. In fact, if you go outside and look at the moon, and you'll see dark areas and light areas. Those dark areas are ancient lava flows on the moon. In fact, I'm going to shift the telescope here a little bit, and this big dark area that you see now, this is called the Imbrium Basin. It's one of the largest impact basins on the moon. In fact, I think it is the largest impact basin on the moon. This is an impact that occurred about 3.5 billion years ago. And it was a pretty big impact. In fact, I think if it was much bigger, it would have destroyed the moon. One of the interesting things about it is this impact was so big and so forceful that the shock wave from the impact traveled outward in all directions, sort of like concentric rings of shock waves going around the planet, and they all went around to the other side and converged at a point on the opposite side of the moon, directly opposite from the Imbrium impact basin. And when we were finally able to see what the other side of the moon looked like, sure enough, at that point, that focal point of the shock waves, the terrain is very jumbled and shattered. And that's because all those shock waves came together at once at that one point and disrupted everything. But anyway, you notice the dark, somewhat smooth appearance of the impact basin's floor. And that is because after the impact occurred, that impact cracked the crust of the moon. And then at that time, the moon still had a molten interior. And so over a period of several million years, magma or lava oozed up through those cracks and filled the basin and created a much newer surface that was smoother. And we see these smooth lava flows on the moon as the dark patches. When we talk about, features on the moon, the man in the moon features, those dark patches are those lava flows. Now, up in the top corner, almost in the middle at the very top edge here, I'll try to move the telescope a little farther north. You see a kind of a half circle. That's called Sinus Iridum. And that was another impact that occurred not too long after the Imbrium impact. And it's a crater that sort of overlaps the impact basin crater. And so when the impact basin filled with lava, it also filled that secondary crater or younger crater. And you get that Sinus Iridum, which means sinus means bay. And then to the right, going a little bit farther over here, you see a round crater that's got another smooth floor. That's the crater Plato. And it's also a younger crater, but it filled with the same lava that filled the Imbrium Basin. All right. Coming down south a little bit, now you see a long arcing mountain range to the right. That's actually the rim of the Imbrium impact basin. And we give names to mountain ranges on the moon. We name them after mountain ranges on the Earth. So this mountain range here is called the Apennines. There's one farther up that's called the Alps and one called the Caucasus. So they're named after mountain ranges on the Earth. One of the Apollo missions actually landed right at the rim. In fact, Richard, if you can put your cursor sort of along there, a little farther down, right about there. There's a channel called Hadley Rill, and that's where Apollo 15 landed. So they were right at the base of the Apennine Mountains, and they collected samples there as well. Now, going a little farther south, and I'm going to center it a little bit more. I got to make sure which direction I'm going here. Whoop, not that direction. So you see a crater with a lot of what looks like splash marks around it. Those splash marks are what we call ejecta rays. And this is the crater Copernicus, and it's a much younger crater, and it was a pretty good size impact from an asteroid. and it threw material out and splashed it all around the crater. You can't see it very well, but there are a number of what we call secondary craters, which was just craters produced by big chunks of rock thrown out of the main crater. And then you see these long, often parallel lines of material that was ejected from that crater at the time of the impact. It's very common for us to see parallel ejecta rays coming out of large craters on the moon. There's some physics involved in why it gets that way. It's a little too complicated to try to explain without using drawings and everything, but it is fairly common. And so that's a relatively young crater. To the left, kind of go.
Speaking of young craters, Little V asks, how often does the moon get new craters, and what is the most recent crater that we can see?
Oh gosh,
That's one for you.
It actually gets hit relatively often, maybe once every few dozen years. It gets hit by a bigger asteroid, but the moon also gets hit by a lot of small asteroids and what we call meteoroids, very small rocks. The moon doesn't have an atmosphere, and it doesn't have plate tectonics. It doesn't have vegetation. It doesn't have bodies of water or anything like that. So when the moon gets hit by an object, it forms a crater, and that crater stays there. So if we were to zoom way in on one of these craters, we would see that there are more craters on top of craters on top of craters. And because it doesn't have an atmosphere, even a small rock, the size of a basketball or even the size of your fist, can make it all the way down to the surface and punch a hole in the surface and make a small crater. Now, the same thing happens to the Earth. In fact, the Earth gets hit 16 times more often than the moon does. But small asteroids or rocks out in space burn up in our atmosphere. And we see those as shooting stars or occasionally fireballs and things like that. Those objects, are maybe the size of a basketball or maybe the size of a small desk or something. They enter our atmosphere here on Earth and they burn up. But on the moon, those objects would continue all the way down to the surface and produce a crater. So in reality, the moon is getting hit frequently. I would say several times a week, probably, but mostly by very small objects. Occasionally, it gets hit by bigger objects that produce craters that are easily seen from the Earth, but that's actually pretty rare. Maybe once every few years, it'll get hit by something that produces a fresh crater that we can see easily with a telescope from the Earth. When was the last one? I can't tell you, but I know every once in a while I'll see some write-up about a new crater that has appeared on the moon. Another crater with a pretty distinctive splash pattern or ejecta pattern around it to the left of Copernicus is the crater Kepler, which is a smaller crater than Copernicus, but it also has some pretty distinctive ejecta patterns. So anyway, that's the moon. We can explore around here a little bit. I don't want to spend too much time because we got to be out of here by 10 o'clock. So we don't want to spend a whole lot of time dwelling on the moon too much. I do want to make sure everybody gets a chance to see the region where the Apollo astronauts landed. So this is it right here. This is the Sea of Tranquility. The Apollo 11 astronauts, the first crew to land on the moon, landed in the Sea of Tranquility down in the kind of the lower left portion of the basin. And that was where the first landing was. So we've seen 2 Apollo landing sites now. So, and then you see a crater right in the upper right corner of the basin. That's the crater Proclass, and it is a crater caused by asteroid impacting the moon at a very shallow angle, so that the ejecta pattern was not kind of uniform in all directions. It all splashed out in the opposite direction as the approach of the asteroid. So you get kind of a butterfly pattern, and that's common with very low angle impacts where it hits at a very shallow angle. All right.
Nice.
So
Okay, a couple of questions.
all right.
One from Tim says, do we have telescopes monitoring the visible side of the moon for new craters? Actually, we have satellites orbiting the moon that probably would catch most of them. Is that not true?
Yeah, we've got a couple of satellites. There's the LRO, Lunar Reconnaissance Orbiter. And I'm sure they're watching for them. And I'm sure if you went to a website for the Lunar Reconnaissance Orbiter, I'm sure they're going to have pictures of fresh craters that they might have spotted. That's the best way to monitor. There are a few observatories who regularly look at the moon, but in all honesty, most observatories don't like looking at the moon.
Right.
It's so bright, and it just takes up a lot of sky. We like it when there's no moon in the sky, because then we have really dark skies, and some of those very faint objects like galaxies and nebulas that astronomers like to look at are best seen when there is no moon in the sky. So there are people who kind of focus on the moon, but a lot of astronomers don't.
Okay, and
Right.
Margaret says, what happens to asteroids after they impact the moon? Well, not a whole lot, I guess.
Well, actually, mostly they break apart.
Yeah.
The reason you get those craters is the asteroid hits the moon, hits the surface, and it initially penetrates in, but it's got so much energy that it literally blows itself apart after it's already penetrated into the ground. And that's what blows that crater out and causes the crater to appear. If it's a small asteroid, the crater will just look like a bowl. Bigger asteroids will produce craters that have a central peak in the middle of them called a rebound peak. And most of the asteroid itself gets destroyed by those impacts. But if you dig around in the right spot underneath, you may find remnants of the asteroid. Just a side note here, in Arizona, about 30 miles east of Flagstaff, there is an impact crater here on Earth. And that crater was formed by an asteroid that had a very heavy iron content about 50,000 years ago. And for years and years and years, there was debate about whether it was an impact crater or a volcanic crater, because there are volcanoes around Flagstaff. And around 1900, a guy named Daniel Berenger purchased the property because he was convinced it was an impact basin, and he was going to find the asteroid, the meteor that hit the ground and produced the impact basin. So he bought the property and then went to the center of the crater and started digging and digging and digging, and he never found it. Now, eventually they proved that it was an impact basin, and eventually they found the remnant of the meteor, but not straight down below the center of the crater. It was actually found deep down in the ground outside the rim of the crater to the south of the crater. And it turns out that was because the meteor, when it hit the ground, it came down at an angle, hitting the ground and burying itself, so that it was actually under the south rim of the crater rather than right underneath the center. So that interesting side story there.
Interesting, yes.
Yeah.
Jasper, one last crater question here. Jasper wants to know, what's the requirements for a new crater to be named? Surely it's not practical to name tiny new craters. I guess you'd have to ask the International Astronomical Union about that. They're in charge of naming everything.
Right. And you are absolutely correct. All the little craters don't get names. Just the big ones that we can see from the Earth. Although even some of those don't have names right now, and periodically somebody will propose a name for a crater in honor of some astronomer or some scientist or somebody special. For example, there are 3 craters in the Tranquility Basin that are named after the Apollo 11 astronauts. Those craters didn't have names before the Apollo mission, but afterwards, the International Astronomical Union named 3 craters just north of their landing site, Collins, Armstrong, and
Aldrin.
Aldrin. Thank you. I'm going to get in trouble for getting his name.
Yeah, right. You might get punched in the face for
Yeah,
that.
you get punched in the face. That's right.
All right. Well,
So much for you getting a crater named after.
Yeah. Well, I think that's enough on the moon.
Yep.
Why don't we go to a few other objects here?
Yep.
While we're doing that, we have a really tough question for you from an 8-year-old named Nova.
Oh.
And
hold that thought.
Would like to know well, this is one that you're not going to answer anyway. It's what is inside a black hole?
Oh, well, actually, what's inside a black hole is called a singularity, and it's a very dense object that's so small it would look like a peppercorn if you could hold it, but you couldn't hold it because it would be way too heavy. And that's called a singularity, and singularities are surrounded by a region of space called a black hole. And that's probably as much as I should talk about it right now. So why don't we pick another object, Richard? What do you say? Mars?
Well,
Mars?
Yeah, I think since Mars is kind of on its way out, we should take every opportunity to look at it.
Yeah.
All right.
We can.
Okay, so we'll go to Mars. Yeah, let's see here. Okay. Well, I might be able to make it in one move without having to resynchronize. Let's see.
Yeah, let's give it a shot.
Pretty close.
See what happens.
Here we go. You're on live view, right?
Yes, I am.
Okay. So our telescope is computer operated. It's our only computer operated telescope. We've got 3 observatories up here, 3 telescopes. 2 of those telescopes are actually antique telescopes, and they are not computer operated. Probably have to go.
Yeah, let me see about getting it centered here.
So although the computer or the telescope is computer controlled, the control system doesn't always sync really well to the sky, especially when we make big moves with a telescope. And we have a relatively small field of view with this telescope. There it is right there. So we have to sometimes hunt around a little bit. We get close to it, but we have to hunt around to get it centered in the field of view of the telescope.
And right now it's only about a little over 68 million miles away.
Thank you. So. 68,000.
No, that would be a little close.
We've been having problems with our zeros over the last couple of weeks. There's just no explaining it, but all right.
Okay, well, there it is. There's Mars. I'm not sure. Are we a little out of focus, or is it just kind of a viewing conditions tonight?
To be determined. Let me at least get our magnification right, and looks like it's a little out of focus, doesn't it?
It does look a little.
That's
it's a little out of shape. Yeah, there we go. It's getting better. Oh,
well, if it got better. Oh, Gerald, are you hitting the focus?
Yeah.
Yeah, it might be easier if I do it.
Okay.
Wrong way. Nope, it's the seeing. Hold on.
Yeah.
Let me try to correct for it on the camera.
So you'll hear astronomers often using the word seeing. And what we're referring to is the quality of the image that we see with the telescope on any given night at any given time. A lot of things affect seeing. Whether or not it's windy, whether or not there's a lot of air pollution in the sky, whether there are clouds, whether there's a lot of moisture in the sky, all of those things can affect the quality of the image that we see. That's not too bad.
Got some detail.
Yeah.
All right.
And often what we get is we get the best we can get, but it doesn't stay good. And you kind of see a little bit of that here. The image will seem to wander in and out of focus a little bit, kind of like you were looking through running water. And that is not unusual, and it's very similar to looking through running water. As the air moves through the sky above us, the air is not uniform density. There's denser regions and less dense regions, and as they pass across our field of view, they slightly change the focus of the telescope, and that's what gives it that kind of swimming, looking through water effect. But we're seeing a fair amount of detail here. We can see some dark regions. Dark regions tend to be rockier, more jumbled, more craters. And then the light regions tend to be more like deserts, kind of smoother, fewer craters, fewer mountains. And that's pretty typical of what we see on Mars. And one of the interesting things is that the dark regions tend to be more in the southern half of the planet, and the light regions are more in the northern half of the planet. Now, Mars has polar ice caps, just like the Earth does. And sometimes we can see them, although I'm not seeing any tonight.
No, not either.
Yeah, I see it flash in and out like every once in a while, but
Okay.
it's not, it's really not very visible.
Yeah, it depends on when we are close to Mars, whether we see one polar ice cap or another, or whether we don't really see either one very well. I think we're at the time.
We're at the third.
Yeah. Yeah. Now Mars is tilted relative to its orbit, just like the Earth is tilted. The Earth's tilt relative to its orbit is about 23.5 degrees. Mars's tilt is more like 25 degrees, so it's actually tilted a little bit more than the Earth is. And because of that, Mars has seasons, just like the Earth has seasons. So sometimes Mars is in a part of its orbit where the North Pole is tipped toward the sun during the daytime. And so it's summer in the northern hemisphere on Mars and winter in the southern hemisphere. And then, a half Mars year later, it's tipped the other way so that the northern polar ice cap is tipped away from the sun during the daytime. And it's the southern pole that's tipped toward the sun during the daytime. And that's when you have summer in the south and winter in the north. Very similar to what goes on Earth. Now, Mars has an atmosphere, but it's a very thin atmosphere. In fact, its density at the surface is 1/100th the surface density of air here on Earth. So it's very thin atmosphere. If you were to go outside without a spacesuit, it would feel pretty much like walking into a vacuum. So not very healthy. But there is enough atmosphere there for Mars to have wind, to have occasional dust storms, dust devils, and occasional clouds.
Great.
All right.
Yep.
Okay. Well, I had a chance to look at Mars. Richard, you had a couple of things you wanted to look at?
Well, I'm wondering if we should just jump into the special object you wanted to look at tonight, because I want to make sure we have enough time to talk about it and find it.
Right. Okay. Well, I understand we have somebody online here named Nova. And Nova, you want to pay attention now because we're going to be looking at a nova. So we're going to do a little pretty long slew here first because we got to get way over to the eastern half of the sky here. So bear with me just a little bit. Whoops. Almost was there. All right, if you want to go to live mode and we'll go to a star that we can sync
Yep.
on, Richard.
Ready to go.
Okay, here we go. So we're kind of going to go halfway to this object. We're going to stop off at a bright star, make sure that our telescope is nice and synchronized. A little off
Close,
to one
but
side. Yep, yep. So.
Perfect.
Oh, you got it.
Yep, I got it.
All right.
Nice blue star. Look at that.
Yeah,
Yeah,
that
it
is strikingly blue.
Yeah. And when we see, when we see blue stars like that, that tells us that the star is very hot. Unlike your bathroom faucets where blue represents cool, in physics, blue represents hot. A star gets really, really hot, it gets a blue tinge to it. And red are the cool stars. So kind of the opposite of what a lot of people think of. You normally think of blue as being the cool color and red as the hot color. But in astronomy, it's just the opposite. So
I wonder how many physicists are confused when they actually go to use the sink.
And in all cases, all stars are hot anyway.
You know, a few years ago, I installed a new faucet in our kitchen. It's one of these things where it had a single handle. You turn it one way and it's blue.
Yeah,
I mean, it's hot. The other way it's cold.
And you were tempted to
just did it. You just said it.
And there was a little button on it that was color coded, right? Blue on one side, red on the other side. And I erased the blue part, so it's all red. My wife constantly gets frustrated with me because she can't remember which way to go.
Well, I'm going to buy you an aloe plant.
All right. So because this object is so small and faint, I'm going to have to do a little different technique for finding it. And that is, I'm actually, rather than pointing out an object in the sky on our sky map, I'm actually going to enter a set of coordinates.
Right.
So I have the coordinates.
And you probably wouldn't be in our database anyway.
No, it would not.
And you said it's magnitude 8, right?
Right. That's what it was last night.
All right.
But it's been brightening.
Okay.
Cool.
We'll have to do an exposure for that.
Yeah,
so,
I'm sure, but let's get it pointed in the right spot.
We got a question. What would it be like to walk into a vacuum, or what would that feel like? Not very good.
It would be the last thing you felt.
Yeah.
Right.
Just before you kind of swelled up. All right, here we go.
Well, let me try to answer some more questions while you're doing that.
Bigger slew than I thought.
Yeah.
I have a question. Why
that
are we
may
not
be
able...
that may be difficult. We may want to do another.
Yeah, let me go to a star here.
Yeah, I'm going to go back to live view.
Yeah, nice bright star here.
Really close.
Yep, it's going to be very bright.
Capella?
Yep.
You're pretty close to Capella, yeah.
Yeah.
There it is.
Yeah.
Top center.
Yep, I see it.
Yeah, let me get the bullseye up.
Well, right on the center line, so we got that part right.
Yeah, that's always good. Okay.
All right.
All right, now let's try to get to
synchronize this.
Wait a minute, we're still centering here.
Yep.
All right, we ready?
Mm-hmm.
Yeah, that looks good.
Okay, here we go.
All right.
Okay, so long exposure. So let me tell you what we're looking at. Nova, we're looking at a nova. A nova is not a supernova. A nova is sort of like the baby brother or the baby sister of a supernova. So what's happened here is you have two stars that are orbiting around each other, a binary star system. One of those stars grew older faster than the other star, and it became what's called a white dwarf. A white dwarf is a very small object. It's the remnant of the star. That once was a full-size star. It has now lost more than half of its mass, and it shrank down. It's very small. It's very compact. It's what we call degenerate matter, but it's orbiting around or with another star that's a giant star. And that giant star is nice and big, and the outer envelope of that giant star is weakly held, gravitationally held by the star. So the white dwarf is pulling matter off of the red giant star.
Very cannibalistic.
Yeah, and what happens is that material piles up onto the white dwarf star. And when there's enough of it that's piled up there, it's mostly hydrogen. And when enough of it piles up, it gets hotter and hotter and more dense and dense. And then all of a sudden, nuclear fusion starts. Now, the fusion process has stopped in the white dwarf, but now you've got one spot on the white dwarf where it starts again. And that creates a tremendous amount of force that actually blows all that hydrogen back off of the white dwarf star and produces a very bright object that lasts for a few days. So, about 3 days ago, in fact, on Thanksgiving Day, an amateur astronomer in Japan was taking images of a nearby open star cluster. And he was using a Canon digital SLR camera, a Canon 6D, and he had a 200 millimeter lens on it. So he was capturing a fairly wide field of view and trying to image this open star cluster. And what he saw was a bright star where there should not be a bright star. So if you look right in the center, you see a bright star. That star shouldn't be there. And as it turns out, that is the star that has gone nova, and now it is very bright. It's actually getting brighter each day. It will do that for a couple more days, and then it will start to slowly fade. So I know it doesn't look like much, but imagine that, just as an example, if you look slightly to the left and down a little bit, you see just barely perceptible another star. That's what this star once looked like. And now it has gotten really bright, and it will continue to brighten a little bit more. And that is the remnant of a star that has gone nova. Now, this will happen probably several times over the course of the next couple million years. And eventually, enough stuff will pile up on that white dwarf that it will actually explode in a supernova. And that supernova is what we call a type 1a supernova. And one of the cool things about type 1a supernova is that they occur at a certain time when the mass of the white dwarf reaches a certain amount of mass. It's about 1.4 times the mass of our sun. And when that happens, the star explodes in a supernova. And because the conditions are so consistent, the supernova explosion follows a set of physical rules that make it so distinct that if you see one of those supernovas, just by looking at the brightness, you can tell how far away it is, because they always give off the same amount of light under the same conditions. And because of that, when we see a Type 1a supernova go off in another galaxy, we can actually use it to measure the distance to other galaxies. And about 25 years ago, two teams of astronomers were doing just that. They were trying to measure the distances to other galaxies using Type 1a supernovas. And as they started analyzing their data, they realized that the data was telling them that the universe was expanding. And it was expanding at a more rapid rate than it used to expand. And that threw everybody off because prior to that, the assumption was that the universe was not expanding faster, that it was expanding slower. And when they realized it was actually expanding at an increasing rate, everybody did some head scratching, and eventually that led to the discovery of what we call dark energy. So, two teams, both of them based at UC Berkeley, were doing that. And one of those teams was led by a guy named Saul Perlmutter, and he eventually got a Nobel Prize for that discovery. Now, the other team was led by Alex Filipenko, who's also a very famous astronomer at UC Berkeley, and he did not get a Nobel Prize, even though he basically made the same discovery at just about the same time. And he wasn't happy about that.
I was just thinking that.
He's a good guy, though. We know him
Yeah,
well.
he's a good guy. He's on our board of directors here at Chabot, and we
he's
do a lot
a really
of things with
good
him.
person.
Yeah,
he should have gotten it.
Yeah. So Gerald, this star is part of an open cluster, so it's fairly close to us, I assume. Do we have a distance on that cluster?
No, I don't have that information. Sorry, John.
Do we have a name for it or something I can look up?
NGC 1582 is the name of the open cluster he was looking at. Now, the open cluster is actually it's out of the frame that we're looking at here. Remember, he was using a much smaller. Actually, wasn't even using a telescope. He just had a 200 millimeter lens on his camera, so he had a much wider field of view. And this thing was off in one corner of the field of view when he did that. So.
Well, it's interesting, though. That means it's fairly close. And if that star eventually does go supernova, it'll be a very bright event for us here.
Yeah.
Great.
All right.
Well, that worked out real well.
Yeah.
Now I have to figure out how to stop the camera. Hold on for a second here.
So
I've been taking frames as you've been talking, so that way I can stack them and make a nice photograph of this.
If we come back in 6 months and take a picture of the exact same region of the stars, that really bright star in the center will not be there anymore.
Right.
Okay, so this open cluster is in Perseus, and it looks like it's about 3,600 light years away.
Oh, okay. All right.
Well, speaking of open clusters, why don't we show people what an open cluster looks like?
You want to go to 37?
Well, I was thinking maybe let's look at M34 this time. I think we looked at 37 last time, and that's in Perseus, so it's close by. And let's see what we can do.
All right.
This is open cluster season.
You want to go to M34.
It's open season on clusters?
Yeah, it's open season on clusters.
I want to go back to Capella and make sure we're all synchronized.
Sounds good to me. Let me get back to frame and focus here. All right. Yep. It's pretty close.
Pretty close. Okay. All right. So we'll go to M34.
This is not M34 that you see on the screen, folks.
M34 is what we call an open star cluster. It's a whole bunch of stars that all formed at about the same time out of a huge cloud of gas and dust.
Oh, this ought to be good. A lot of
There
interesting
we go.
doubles in here.
All right.
All right.
So we're
Ready?
going to have to do a long exposure. Yeah, we're there.
Yeah. Okay.
So open star clusters, there's actually quite a few of them out there. In fact, some of them are even visible to the naked eye. They are groups of stars that all formed at about the same time out of a huge cloud of condensing gas and dust. And that's how stars form. They don't form all by themselves. They form in clusters. And eventually the gas and dust dissipates after the stars have formed, leaving behind sometimes several hundred stars that are all kind of drifting together through space, orbiting around the galaxy. And eventually the stars separate from each other. That's how our sun formed, and that's how just about all the stars that you see in the night sky formed. And we call them open clusters because they are just a whole bunch of stars close together. And they don't really have any kind of a pattern to them
Or shape.
or shape.
Yeah.
The other kind of cluster is called a globular star cluster. Globular star clusters look like balls of stars. And instead of all of the stars drifting more or less in the same direction together, in a globular star cluster, the stars orbit around the center of the cluster. So this is an open star cluster. Now, for those of you who don't have easy access to a telescope, you get to see an open star cluster. In fact, right about now, if you look out to the eastern sky and look about 3/4 of the way up, you might see what looks like a faint little grouping of stars that some people mistake for the Little Dipper.
We've had problems with that before. I'll talk to, or I'll have Gerald talk.
Hold on, you guys.
Why don't you
You're on
mute? Why don't you
microphone.
mute,
I'm sorry.
John?
I'm sorry. I should have.
Yeah. Sorry about that, folks. So anyway, it looks like a little miniature Little Dipper, but it's actually an open star cluster called the Pleiades, and it's actually something you can see with your naked eyes pretty easily, even in poor seeing conditions. It shows up pretty well. And in binoculars, it's great. It actually has a little bit of a bluish tinge to it because there is a cloud of gas between us and the cluster. So the light from the cluster lights up that cloud of gas and gives it a very ethereal appearance. And that's another open star cluster like the one you're seeing here.
That's up pretty close to the moon right now, though, so it'd be hard to see until tomorrow night or the next night.
Probably wait a couple of nights.
Yeah.
Full moon is going to be very early Monday morning. So you might want to, wait a couple extra days and then look up to the high in the eastern sky and look around for that little clump of stars. That's the Pleiades. Now, when you look at the Pleiades, if you look carefully, you might notice it looks a little familiar. And if you own a Subaru car, it ought to look really familiar. In Japan, the Pleiades is called Subaru. And if you look at the emblem on the front of a Subaru car, it's the pattern of stars, the brightest stars in the Pleiades star cluster. In fact,
it might look familiar for other reasons too. It's used an awful lot in movies and television.
Yeah.
You very often see the Pleiades up there on the big screen.
Should we look at the Pleiades?
Yeah, let's give it a shot. We'll see at least some big, bright blue stars.
Okay.
Which are hot, not cold.
Yeah.
Right.
The only problem we're going to have is that
it's too big.
It's because it's relatively close. It's only 420 light years away. So because it's so close, we're not going to be able to get the whole thing in our field of view.
We'll just get a little piece of it.
Yeah. Plus, we're pretty close to the moon. In fact, we actually may have a problem because of the moon.
Yeah, we're going to get some glare off the moon for sure.
Yeah,
but
well, we'll give it a shot and see what happens here.
Nothing ventured, nothing gained.
Right? M45, right? Where are we?
Yeah, while we're moving, I did want to point out something that John had mentioned earlier about the open cluster you see on the screen, which this one has a lot of double stars in it. You can see, in fact, here's a pair, And I'm not sure about these two, but certainly this is a pair, a double star pair right here.
There are some more outside of what we
outside of our
figure
field of view. Yeah. All right. Let's give it a shot.
Rick said that's why he bought a Subaru recently. I guess he was so impressed by the Pleiades that he bought a Subaru.
All right, well, we're there. Let's see what we see here. We may have to wander around a little bit, taking multiple images.
One star in the Subaru.
Yeah.
We'll have to slew to each of the 7.
Yeah. Okay, well, I think we'll go east here a little bit.
All right. Tell me when.
All right, go ahead and give it a shot, see what happens. So Richard is doing timed exposures. So these are kind of like long exposures. When you're doing astrophotography, you do a lot of long exposure work because the stars are just too faint to pick up in a, fast image like you would take, when you're taking portraits or something.
Oh, we're getting there.
Got one of the big ones.
All right.
Hey, what? Just for grins, let me put it on live view.
Yeah, you might.
And let's see, it may be sensitive enough to get more than one of these,
There
right?
we go. All right, we got it.
Yeah. So let me
All right.
Yeah, I could kind of hunt around a little bit.
hunt around and then take an exposure to fill it in.
Well,
what do you think?
I just see the.
Why don't we?
Which way you're trying to go? We can't tell you.
Yeah, why don't we take this area here and kind of move it over to the center?
Oh, okay.
And let's see if a longer exposure gives us anything. Okay, stop right there, I think.
All right.
Yeah. Let's see what that does for us here.
There are quite a few stars. Most of them are fairly dim. The cluster has, I think, over 1,000 stars in it.
It looks beautiful in binoculars. Binoculars have a much wider field of view, so you can get the whole thing in the field of view of a pair of binoculars, and it's just really cool. I'm surprised
there we go. Let's get a little bit more.
Surprised we don't have more moon glare.
Yeah, it's not too bad. Probably can cut down the exposure time on this too.
Sabina wants to know, are double stars typically the same size, roughly, or do they tend to be uneven in size?
Oh,
There's all kinds of answers to that, I think.
That's a good question. I think they really come in all varieties, right?
Yeah.
And there are some that are identical and others that are completely different. It's all a matter of how they formed from the cloud of gas that they formed from, and if one was hogging more material than the other, it will end up being a hotter, larger star than the companion.
Somebody else asked, how do double stars form? Actually, it's very common for double stars to form. Remember how we were talking about how clouds of gas and dust condense and form new stars? It's very common for those stars to form close enough together that they start orbiting around each other. In fact, probably half or more of the stars that you see at night with your naked eye turn out to be actual double stars, or even sometimes triple stars or quadruple stars. One of the famous double stars that we look at is called Albireo, but it's actually, those two stars are not actually orbiting around each other, at least we don't think they are. But one of those stars is a double star where the two stars are so close together that looks like one star. And even in the telescope, it looks like one star. But when we analyze that star spectroscopically, we see two spectra that are moving back and forth relative to each other. That tells us that there are actually two stars there. they're so close together. They, look even in the telescope like one star.
All right.
All right.
I think
Well,
let's go to questions and see if anybody else
oh
has.
yeah, we're getting towards the end
We're
here.
at 10, so we're on a
Yeah,
little bit of
so
a constrained schedule these days. We normally would go for another half an hour, but we're
well, let people, put in any questions that they have. While they're doing that, I just want to remind everybody about our donation button on our Facebook page, or going to the Chabot website. There's a donation button on our website, chabotspace.org. We encourage you to help us out. Our virtual programming, we're not open to the public, so we're doing nothing but virtual programming right now. And we do continue to need support. We don't have the admissions that we would normally get when people come up here. So we rely a lot on those donations. And in addition, if you go to the Chabot webpage, chabotspace.org, and get yourself a new membership between now and December 31st. Anybody that gets a new membership, Chabot will automatically give a new membership to a local teacher at one of our local schools here in Oakland. So you can, get a membership and get the benefits of a membership and help out a teacher here in Oakland.
Tim had a question. Seems there is a comet south of Capella. Very true. 311P Pan stars. Are comets visible through Nellie?
Yes.
Yep.
Yeah.
And sometimes we look at them, and probably sometime this season we'll have an opportunity to take a look at a comet.
Yeah, sometimes you hear about comets, and especially after Neowise that we had a few months ago, which was bright enough to see with the naked eye, that tends to spoil you and think that all comets are like that. Actually,
most are not like that.
most of them are. If you don't have a powerful telescope and a good camera, you're not going to see it. So. But astronomers like to talk about them because they do have telescopes and cameras. So you'll hear about that quite a bit.
We also had a question about how much bigger are these stars when we were looking at the Pleiades than our own sun. And I was just looking up one of the brighter ones. It's about 2.2 solar masses. And
which makes it a lot more.
1.5 times the diameter of the sun.
Yeah.
But very, very bright because they are hot stars.
Right. So the more massive a star is, the hotter it burns. And the hotter it burns, the faster it uses up its fuel and the shorter its life is. So, our sun is what we sometimes call a yellow dwarf. And its mass is comparatively low to a lot of stars. And the lower the mass is, the longer the star lasts. So, we're kind of lucky that we don't have a really bright star, So there's always an interesting thing, we call most main sequence stars, stars like our sun, or stars even a little more massive, and certainly a star less massive than our sun. We call them, when they're on the main sequence, we call them dwarf stars. And we also have this designation of planets called dwarf planets. And some people think, well, if it's a dwarf planet, then it's not a planet. Well, that's like saying if our sun is a dwarf star, it's not a real star. So dwarf stars are real stars, and dwarf planets are real planets.
And dwarf people are real people.
Yes, there you go. All right. So Pluto is a dwarf planet, and therefore it is a planet.
All right. I knew that was coming. I was waiting.
Take that, Neil deGrasse Tyson. All right. Any other questions?
I think that's it.
That's about it.
Okay. Well, thank you, everybody. Hope you enjoyed it. We will do this again.
Hope you've enjoyed your holiday weekend, and we'll see you next week.
And 9 o'clock next Saturday.
Coming, and see you later.
All right. Good night.
Bye-bye.